Third, that matches up. See if you could find where I went wrong. What happened here? 4x times negative 3, x squared minus 4x plus 4, or negative 16x squared. That should be 12x, I agree with that. I think I did this right. Let's see. All right, let's match up to see. We got 6 terms up here. Let's see if these 6 terms match up with these 6 terms. They got a 4x to the third. We got that here. Check. All right. We got a negative 3x squared. So did they. Check, check. They got a negative 16x squared, and so did we. All right. They got a positive 16x. Well, so did we. So far, so good. They got a negative 12. We got a negative 12, but uh-oh. I see an issue. When we multiply negative 4x times negative 3, we got positive 12x. This student got negative 12x. So, is the following proof valid? Well, I don't really think so, but we have to explain why. All right, so the way that we would explain this on a Regents would be, is the following proof valid? We got to answer the question. No. Not a valid proof because when negative 4x is multiplied by negative 3, you should get 12x, not negative 12x. All right. Okie dokie. All right. I'm going to skip over number 7. I'm not really in love with that question, but I do like number 8 because those of you that took geometry last year, which is pretty much all of you have taken geometry at some point. Most of you took it last year. This integrates a little geometry action into Algebra 2. So it says sometimes identities can have geometric connections as well as algebraic. The Pythagorean theorem gives us ample identities. And those of you that were lucky enough to have me last year definitely remember Pythagorean theorem, right? Think about it. What's Pythagorean theorem? I think it's a squared plus b squared equals c squared. Do you remember what you used that for? Remember these guys? Right triangles, where you have 3 sides, obviously, of the right triangle. Remember what this guy was called across from the right angle? This was your hypotenuse. All right. And then we had 2 legs. All right. The C is always the hypotenuse, and the 2 legs are always the A and B, and those ones are interchangeable. But the hypotenuse always has to be C. All right, and I'm pretty sure all of you kind of remember that. Hopefully, actually, you'll probably remember that for the rest of your life. A squared plus b squared equals c squared. All right, so exercise number 8 says Jerome uses the polynomial identity. Whoa, look at this mess. X squared minus y squared plus 2xy squared equals x squared plus y squared to generate the Pythagorean triple 9, 40, 41. What values of x of y did he use to generate the values for the 3 sides of the right triangle? So, let's think about this. It says to generate a Pythagorean triple of 9, 40, 41. What the heck is that? Well, remember there were those special right triangles that your teacher or me used to talk about? This one popped up quite a bit. The 3, 4, 5 job. This one popped up a bunch. The 5, 12, 13 action. Okay, the Regents loves these two triangles. I drilled that into your heads. Okay. Well, one of those other special triangles that pops up is the 9, 40, 41. Okay. Because if you plug this into the Pythagorean theorem, okay, and let's just do a little test run. 9 squared plus 40 squared equals 41 squared. All right, let's check that out. Well, 9 squared, I remember. 9 squared is 81. 40 squared is 1600. And 41 squared is 1681. And guess what? When you add this side, you figure out that, oh, this makes sense. Okay. So 9, 40, and 41 can be the three sides of a right triangle. All right. Now, what is this mess that they gave us here? This looks pretty ugly, but it's not. Here's why it's not. I just stabbed myself with a pen. Oh my gosh. You bleeding? No, not bleeding. Here's why it's not too ugly. All right. We basically have the Pythagorean theorem here. We have a number squared plus a number squared equals a number squared. So this is your A, this is your B, and this is your C. Okay? X squared minus y squared is A, 2xy is B, and x squared plus y squared is C. This is the Pythagorean theorem. A squared plus b squared equals c squared. So, what the question is asking us, this is kind of a little guess and check job here. All right, it's asking us, when I plug in one of these four choices in for x and y, I should get 9, 40, and 41. All right, let's check out when x equals 3 and when y equals 4. Okay, I'm going to do that trick. Remember that trick that I taught you a while ago where you can store in numbers for your calculator? All right. Well, we can do that here with x and y. We're going to plug in 3 and store it in for x. And then we're going to take 4 and store that in for y. The way that you get y is you press this green button, alpha, and you go down here, the 1 button, and that'll store that in for y. All right, and we're seeing if that, when I plug these 3 in for x and 4 in for y, okay, this one needs to turn into a 9, this one needs to turn into a 40, or vice versa, and this one's gotta equal 41. So let's try x squared minus y squared. Let's see what that comes out to. And now I could just plug that exactly into my calculator since I stored the numbers. So let's see what x squared minus y squared is. -7. Oh yeah, that makes sense. 9 minus 16 would be -7. Is -7 9, 40, or 41? Definitely not. So these ones don't work. Okay? When I plug these numbers in to this equation over here, I should get 9, 40, and 41. Alright, so let's try choice 2. And now we're going to reset it and plug in 9 and store that in for x. And press enter. And then we are going to store in 40 and store that in for y. Okay. All right, so let's plug in x and y in for this number here. X squared minus y squared. X squared minus y squared. And I get, whoa, negative 1,519, which definitely is not 9, 40, or 41. So my answer definitely can't be choice 2 either. All right, let's check choice 3. I'm going to store 4 in for x. 4 store for x. And we're going to store 5 in for y. 5 store for y. All right, and let's see what x squared minus y squared is. X squared minus y squared is